All right, good morning, and welcome to today's class. Today we will talk about the last session about data management, handling categorical data, or how to pre-process categorical data. It is often useful to measure objects in terms of their quality instead of quantity. The variables that are used to measure these features of some individuals are called categorical variables. For example, gender, color, brand of cars. So these are all categorical variables, right? And there are two types of categorical variables, uh, nominal and ordinal, right? For nominal categorical variables, the categories are nominal, so there is no intrinsic order uh, between or among the categories. For example, colors, right? Blue, red, green, etc. Right? Um, and also types of fruits, banana, strawberry, apple. So if there is no intrinsic order among the categories, then the variable is called nominal variables. And the other type is called ordinal variables. Okay? When the categories of the variable has an intrinsic order, for example, low, medium, high, young, old, agree, neutral, disagree. Okay? So it's kind of important to determine which type of categorical variable a variable is, because it will be related to how to encode these variables, how to encode the categorical variables into numeric variables. And machine learning models often require that the input to be numeric values, especially in Python, Python packages. The models always assume that the inputs are numeric values, so they just cannot accept any character strings. In that case, before we feed our data into the model, we have to encode categorical variables into numeric variables. And also how to encode these variables, it really depends on what type of categorical variable we have. Okay? And of course, in the process of transformation, we'll try to retain the original as much as information as we can. For example, for ordinal data, we'll try to keep this information, like the ordering among the levels. Okay? For nominal data, there is no intrinsic order, then we probably, we have to transform them in an appropriate way too. Okay, so let's see. So first, let's take a look at nominal categorical features. Okay. One way to, so for nominal categorical variables, we will just create dummy variables, basically binary variables, one and zeros, for each category of the variable. So for example, if there are C levels or C categories for a variable, then we will create C dummy variables. Or sometimes we say C minus one dummy variables. But in Python, it doesn't matter that much. Actually, the redundant dummy variable will be ignored during the fitting process. And one way to one-hot encode or creating dummy variables is to use Scikit-Learn's label binarizer. So this is one way. So we first need to import the function, a label binarizer, from this pre-processing submodule from Scikit-Learn again. And we create a small toy data set called feature with only one column. So you see the values are character strings. They are states in the US. Okay, so definitely they are not ordered and no intrinsic order among them. So this is a nominal variable. Right? So we first need to, again, instantiate the encoder or the transformer. Right? We just use the default parameter values, call it one hot. Right? And then we can apply the fit transform method to encode the feature matrix. So, and save the result in feature T, right, which stands for transformed feature. So let's run this. So see, 3 columns of dummy variables are being created. Right? So that is because in our data set, there are 3 levels, 3 unique values, Texas, California, and Delaware. Right? So it really depends on how many unique values are contained in our data matrix. And the logic is like this, okay? By the way, automatically it orders the values alphabetically. So the first dummy variable is corresponding to California. So if a row, if an observation is corresponding to California, then it will be 1, otherwise 0. Right? And the second column is the dummy variable for Delaware, and third one is for Texas. So California, Delaware, and Texas. So let's verify it. So the first value is Texas, right? Then the first row in the new data matrix is corresponding to the first observation Texas. Okay? And indeed, okay, the third dummy variable is equal to 1. The first 2 are equal to 0. Okay? So this means this is corresponding to Texas. And second row, the second observation, C is equal to 1, California is equal to 1, right? So that's because the second value is indeed California, right? And D and T are equal to 0. Right? So this is called one-hot encoding because it's kind of like a switch. Dummy variables are kind of like switch, either 0 or 1, right? So for each, after the transformation, for each row, only one of the dummy variables is equal to 1 always. Right? You see, if you observe all of these, only one of them is equal to 1. So that means only one is hot. The rest of them are cold. 0 means cold. 1 means hot. So this is one hot encoding. Then so we can use the classes attribute to output the classes. Right? Namely, you can take a look at the ordering, the actual ordering. So it's California, Delaware, and Texas. Right? So it must follow a way to order the dummy variables in the transformed feature matrix, right? So this is a default ordering, alphabetic order. And you also have the option to reverse the one-hot encoding. So namely, you can convert the transformed feature matrix back to the original features matrix. As you see, you can use the inverse transform function to convert it back to the original vector. All right. Another way to one-hot encode these nominal categorical variables is to use the pandas package. Okay, so import pandas as PD, and then you can just call the getDummies function. Okay, so let's run this. Okay, we will use this function. So then we have this. This is the new features matrix. So you see the underlying logic is the same. It will create a dummy variable for each unique value, for each distinct value in the original features vector. And also the dummy variables follow this alphabetic order. California, Delaware, and Texas. Okay. And personally, I prefer this function because it automatically creates column names in the result in the new features matrix. And also the result is a data frame. So it's very convenient. You can calculate some summary statistics using this data frame, using the pandas, using the functions in the pandas package. So it's kind of convenient. And then let's move on to the second type of categorical variable, ordinal categorical variables. For example, the Likert scale, strongly agree, neutral, disagree, strongly disagree. Apparently, there is an ordering among the categories. So when we encode this kind of ordinal data, we try to retain this information. We don't want to lose this information because they are kind of linear. It's kind of very useful. At least monotone increasing. May not be linear. So in order to keep this ordering information, we can create a mapper. Okay? A mapper is actually a dictionary. We know how to create a dictionary, right? So we can, if we want to do it in a very flexible way, okay, you have the full control of how to convert your category, your ordinal data into specific values. If you want to have a full control, then use a dictionary to do the mapping. And let's see one example. So we create a small data frame with only one column, which is score. So this variable only has 3 levels, low, medium, and high. So they are all strings, right? And suppose we want to convert these letter scores into numeric scores. So one way to do it is to create a dictionary. Okay? We can call it a mapper because we will use it to map string values into numeric values. So it's just a dictionary. A dictionary is a set of key value pairs. So the keys are corresponding to the original string values. So see low, medium, and high. And then you can decide which numeric values you want to convert them to. For example, I just convert them to 1, 2, and 3. Okay? And don't forget the comma to separate them. Okay? So we can call it scale mapper. Okay. And then we can use the replace function to replace the values. Okay. Remember, we have seen this function before, right? The replace function. It will replace the original value with a new value. Right? Remember, we used to use a missing value to replace all the male characters in the sex column in the Titanic data set, right? So now we just defined a mapper, right? How to do the replacement. Right? Replace low by 1 and medium by 2, high by 3 for all of the values in this column. Okay? So now let's run this. You see this is a result. Okay, 1, 1, 2, 2, 3. The original one is low, low, medium, medium, high. So after the transformation, we have 1, 1, 2, 2, 3. The first column is row indexes, right? So don't be confused. So it is a very flexible way to convert ordinal data into numeric values. Alternatively, we can use this function, ordinal encoder function, in the preprocessing submodule. Right? So for nominal data, we use one-hot encoder, right? But binarizer, high binarizer. but for ordinal data, there is a corresponding function too. So we can instantiate this encoder, just leave it open, so use the default options, and then just you can fit and transform. You can also fit and transform at the same time. So let's see what happens. So apparently it does not look very correct, right? So we have low, low, medium, medium, high, right? But they were encoded to 1, 1, 2, 2, and 0. Apparently, by default, it will use 0, 1, and 2. But clearly the ordering is not correct. So it turns out that by default, it used alphabetical order. So it's order the levels like high, low, and medium. So convert high to 0, low to 1, medium to 2. It's apparently wrong, right? So we cannot leave it open. Okay, we cannot use a default option. So instead, we can specify the true ordering. You can do this, specify the categories arguments in the encoder, right? Specify the true ordering, right? From low to high. Okay? Call it ordinal encoder 2 and fit and transform our data frame. Okay? So now we have the correct transformation. Right? All right. And if we use this kind of encoder, it's kind of very convenient but very rigid because the numeric values are chosen for us, right? So the function uses 0, 1, 2. Okay? Imagine if you have 4 levels, then it will use 0, 1, 2, 3. Right? So it assumes that there is a kind of the difference between any 2 adjacent levels is the same, is 1. Right? So it's kind of a linear pattern. If this is not true, then we need to go back to our manual way. Okay, for example, suppose our data frame has an additional level called barely more than medium. Right? So the data frame looks like this. There is a level like this. Right? Apparently, it won't be very intuitive to use an integer in between median and high. Right? Just one integer. Like if you code it like 0, 1, 2, 3, then you assume that the difference between median and barely more than median and the difference between median and high are the same, which does not make sense, right? So in this case, we should not use the ordinal encoder directly. Instead, we should create our own mapper. For example, we can transform this level to 2.1 instead of 3. So then we can encode it in the way we like. Okay. All right. And so this is one hard encoding. And notice that even if we use the replace function, the original data frame will not be changed. Right? So for example, if we type this, even after the encoding process, the values are still the same with before it is encoded. Right? So that is because, as I said, in pandas, it always create a new copy of the data frame. If you do anything to a data frame, it will create a new copy, but the original one will not be changed. If you want to save the new copy, you can save it. Alternatively, we can add an argument in place equals true. Then it will change the original data frame. So let's see. So for example, we can add this, and then let's type this to see if there is any change. It has been changed. this is not always recommended, as I said. We'd better keep the original data frame intact. And if we want to save the result of any operation, just create a new data set, create a new data frame, save the result. All right. And next topic is imputing missing class values. In last lecture, we learned how to impute numeric values, right? So now let's take a look at a categorical data if there is any missing value. So one solution is to use the statistic to replace the missing values. For categorical data, the most intuitive one is the most frequent value in the column, or the mode, right? The most frequent value, which because for categorical variables, the mode has the most frequency, and it is supposed to be the most representative value among all of the values. So it makes sense, right? So this is kind of like a simple imputing method. And still import the simple imputer function from the input submodule of Scikit-Learn. And then let's create a toy data set so the first 4 rows do not have any missing values. And the last 2 rows has a missing value in each row. So see, have a missing value in each row. And then we stack them together. I vertically stack them together, call it X complete. The reason that we create them separately is because later on, we will use machine learning model, basically k nearest neighbors to impute the values. In that case, in the training part, in the fitting part, we can only feed complete matrices into it. Okay, so it's not the KNN imputer anymore. Okay, it's a classifier. Okay? It's a real classifier. Okay? So we'll see a little later. But anyway, don't be surprised. You might be curious why we created them separately. Right? There is a reason. Okay? So anyway, this is a complete data frame, a feature matrix. Then instantiate the imputer. Right? Simple imputer strategy is most frequent, which means the mode. For numeric variables, we use median or mean, right? But for categorical variable, we use most frequent. I just call it imputer and fit transform our data set. And then you see that 1 is used to impute the missing values. That is because you see among these 4 values, right, 1 is the mode. 1 has the biggest frequency. 3, 1, and 0, 1, 0. So definitely we should use 1 to impute the missing value. So this is the simple imputer. Alternatively, we can use machine learning models to predict missing values in any column in the data frame, right? So instead of using KNN imputer, because the KNN imputer last time, the imputer that we learned last time is designed for numeric values only, numeric data only. It cannot be used to predict labels, right, or categorical variables. So we will actually use the machine learning model, like k neighbors classifier, so to do prediction. So to do it, we first need to instantiate the classifier, called a function. Oh, by the way, the function is from the neighbors submodule in Scikit-Learn. And we instantiate it. So we use 3 neighbors this time. So k is equal to 3. And weight is distance. And then we can fit the model. again, as I said, most machine learning models, actually all machine learning models, cannot take missing values directly. Forget about KNN imputer. Okay, so that is not a machine learning model. It is a imputer that uses a machine learning model. Right? So that one can accept missing values because it is used to do that to impute values, right? But a regular machine learning model in Python will not accept missing values. So that's why when we create the features matrix, we separate them, right? One part does not have missing values. The second part has missing values. Right? So notice that we only feed the first matrix to it. Right? And also when you call a machine learning model, you have to separate the features matrix and the target column. So the first argument is the X matrix. The second argument is the Y vector. Right, so notice that when we create them, they are together. Right, so this is this is the column with missing value, which is the first column. Remember, the first column has missing values in the second part. Right? So we treat it as a target vector. Right? And then train the model, and then we can do prediction for the part with missing values, right? And pay attention, we just feed the part without missing value, which is treated as a features matrix. And then we can save the result in imputed values, right? Same result. If we use K and N, we get the same result, right? 1 and 1. Okay? So the K neighbors classifier can help us to predict categorical values, okay, or factor values. Right? So it's 1, 1. And then we can do some more data manipulation. So we first make the imputed value as a vertical vector, and then horizontally stack it with the part without missing values. Right? So this is the kind of the second part without missing values with imputed values. Okay? Then furthermore, we can vertically stack the part without missing value and the part with missing value together. So this will be the complete feature matrix after the imputation. Okay? So it requires some work, apparently, because there is no KNN imputer for categorical variables in Python. Right? And alternatively, we can use it, right? But you see the imputed values may not be an integer because the response variable is assumed to be continuous numeric. So you can still do it, but you need to do some extra work. Namely, you need to round the result to an integer. Right? So the first imputed value is 0.88. If you round it, you will get 1. So you can round it to a whole number, so you get similar result. Yeah, I think it is in general okay. Even if you have multiple categories, for example 0, 1, 2, right? You can still use the KN imputer and then carefully round the result to an integer, right? Either 0 or 1 or 2, and then that will be your the best imputed values. Right? So either way is fine, but theoretically, we should not use this because this is for numeric values. All right. Then let's continue. As I said, I emailed you this morning. The quiz starting time of the quiz has been postponed to 11 a.m. And because I know that I cannot finish everything in 30 minutes. Okay, so don't worry. Okay, the quiz will be open at 11. You will have sufficient time to do it. All right. Then let's move on to the last part, handling imbalanced data. Sometimes the target vector is highly imbalanced, which means, for example, we have 90% of zeros and 10% of ones in your data set. Or there are more extreme cases, especially in the insurance industry. The probability of ones probably is just 0.1% and zero is 99.9%. Yeah. So highly imbalanced data. In this case, it creates a lot of difficulties in fitting a machine learning model and to have a high quality prediction. So especially for the smaller class, right? For the, for example, 0.1% class, it's very difficult to make good predictions because uh, the sample is too small. Okay, it's too small. And how to manage this situation on highly imbalanced classes, right? There are a few strategies. The first one is to collect more data. So if it is possible, we can collect more observations for the smaller class. But unfortunately, it might not be feasible in practice always. Um, and the second strategy is to change the metrics used to evaluate your model. So we do nothing about the data, but we consider more metrics when we assess the model. So why do we need to change the metric? For classification problems, the most commonly used metric to evaluate this kind of model is the accuracy. And the probability of making a correct prediction, accuracy. However, if the data is highly imbalanced, for example, there are only 0.5% of observations have some rare cancer, and 99.5% of patients don't have the cancer, right? Which is very intuitive, right? Because it is a rare cancer. Right? In this case, even a very naive model can have a 99.5% accuracy. Why? Because you can just make a model like this. Okay? Given any new observation, predict that the person does not have the cancer, has that type of cancer. Then 99.5% of chances you are correct, because in the population only this many are healthy. They don't have that cancer. Okay? So accuracy won't work. It won't be a good metric to evaluate the model. So in this case, we should consider some other metrics that can evaluate your model in a more comprehensive way. For example, you can create a confusion matrix or calculate precision, recall, F1 scores, etc. Okay, so they and also ROC curves. So they can help us to evaluate the accuracy in the small classes in a more effective way, a more precise way. And the third option is to use the class weighing parameters included in some models. Right? Some models have this argument, class weight, this parameter. You can set it to be true, to be equal to balanced. Then in the process of model fitting, they will try to increase the weight of the smaller class and decrease the weight of the larger class, okay, so that the result will be more balanced. Okay. And the last two strategies are downsampling the larger class or upsampling the smaller class. So these are kind of manual ways to handle this imbalanced class situation. So let's take a look at downsampling. So in downsampling, we create a random subset of the majority class of equal size to the minority class. So for example, we have, we have 100 observations of 0 and only like 10 observations of 1. Okay. So in downsampling, we will draw a random sample of size 10 from the larger class. Okay. And then combine these two together to have a perfectly balanced data set and then fit the machine learning model. So this is called downsampling. Of course, this is not a good idea because we will waste a lot of observations in the larger class. Right? We shrink the sample size, which is in general not a good idea. And upsampling, the opposite. Right? So again, we have 100 zeros and 10 ones. Right? In this case, we will do resampling of the smaller class with replacement, and so that the sample size is equal to the larger class. Resampling. So in this case, we must allow replacement, right, so that we can essentially enlarge the size. But pay attention, the variation won't be changed, right? So, so this is another way. And there are some examples. There is one example about it. So let's finish this part. We will use the iris data set. So this one contains 3 balanced classes of 50 observations. So 3 classes, each one has 50 observations in the iris data set. Three classes, completely balanced. And we will manipulate the data a little bit. We will get rid of the first 40 observations for class 1, the first class. So then consequently, we only have 10 observations for the first class. And we also will combine the second and the third class together so that we have 100 observations in the second class and code it to 1. And this is 0. Originally, these are 0, 1, and 2. Right? We combine them together to get 1. Right? So that we create a imbalanced data set. Right? So this is what we do here. Right? So see, we import the iris data set and load the features matrix and target vector. And then we subset the features matrix and target vector, right, by starting the index from 40 and then to the end of the data set. And so basically, we got rid of the first 40 observations. Right? And then we recode the target vector. You see, we use a where function. So if target is equal to 0, then 0, otherwise 1. So namely, we combine the second and third classes to 1, right? So that it's a binary problem after this step. Okay. And then let's see how to do, let's skip this, how to do downsampling. Right? So we first save the indexes of zeros and ones in I class 0 and I class 1. Right? So you see, we use this conditional to select the indexes of these observations, these target observations. Right? So I class 0 basically are integers like 1, 0, 1, 2, 9. Okay, actually, and I class 1 will be what? Will be 10, 11, all the way to 109. Yeah, so totally 100 indexes for class 1 and 10 indexes for class 0. And then measure their length. And class 0 will be 10, and class 1 will be 100. Okay. And then we use this random choice function to select 10 indexes from I class 1. Okay, so basically, select 10 numbers from this set. Okay, replacement equals false because we are doing downsampling. Okay, we are sampling 10 from 100 indexes, so we don't allow replacement. Okay. Then save it in here, I class 1 downsampled. So this set contains the indexes that we will that for the downsampled class 1. Okay, downsample class 1. And then we can use them to choose observations for class 1 target values, right? And combine them with class 0, original class 0. So 10 plus 10. So now 20 indexes. Okay. And next, we can use them to select features, the rows in the features matrix, and then combine them together. Oops, sorry, I forgot to run the previous code. So see the indexes, the target values for the new data set. It completely balanced now. And also then, so we vertically stack the features matrix for the class 0 features and class 1 features. Right? So these are the first 5 rows. Right? So this is downsampling. Upsampling works similarly, but so now we will choose from I class 0. I class 0 is what? Is the small set 0, 1, all the way to 9. Okay. So size is equal to n class 1. N class 1 is equal to 100, remember? So we will sample 100 indexes from this small set of 10 indexes. Of course, we need to let replace equals true. Okay, so this is called resampling. Okay, so we manually increase the size. Okay, and then we can, so you see, after we do it, so this is the target, the new target vector, 100 zeros and 100 ones now, okay? Because we resampled, yeah, 10 times. Okay? And similarly, we can vertically stack the zero class, the new zero class features and the 1 class features. So now the features matrix will have 200 rows. Originally only have 110 rows to 200 rows. We enlarge the smaller class. All right, perfect. I think we can stop here.